Good evening, everybody. Welcome to our new E.M. Ramsey Center seminar this evening. Thank you very much for coming. Today we have Andrew. I'm sure you all know of him by now. He will give a talk on why matter matters. And I wonder, if I asked you, what does matter mean? How many of you could tell me? So I hope at least one can tell that. So Andrew is research director of the E.M. Ramsey Center for Science and Religion. And is a member of the Theology and Religion faculty here at Oxford and research fellow at Harris Manchester College. He received a doctorate in physics from Oxford, studying at CERN in particle physics, and another doctorate in philosophy, studying at St. Louis University in the States, and as well has degrees in theology and philosophy from the Pontifical Gregorian University in Rome. So hopefully tonight we'll understand why matter matters. So Andrew, all yours.
Thank you very much. I'll preface my talk by making a few introductory remarks to manage your expectations. I'm not going to suggest that in dynamical systems there's some spooky religious matter, and it's really, and of course, quite a few of you may be already familiar with some of the subjects with some of the work done in chaos theory and so on. Perhaps I could just gauge from you, have you heard about chaos theory, emergent systems, and so on? I get about half or so, maybe slightly more than half. Okay. In my experience, the discovery of chaotic work done on chaotic systems, dynamics, became very exciting in the 80s, with lots of books being published and lots of pretty pictures. So this is a pretty picture here. I'll explain a little bit about that later. And all these sorts of things are all over the internet, strange attractors and so on. And then people didn't really know what to do with them, you know. So they're kind of weird. And then they've just, to some extent, we've more or less carried on as before. And I take a general interest in physics. I have done since being a particle physicist myself. And I've been very struck for a long time of how little grasp we have of what matter is. And I think there's a relationship between chaotic systems and matter, which needs to be teased out and which is not being talked about very much. As regards the impact on philosophy or theology, to an extraordinary extent, what goes on in physics inspires philosophical ideas, and what goes on in philosophy shapes the world of theology. So for the last few centuries, to an extraordinary extent, the systems developed by Newton for looking at the world influenced all kinds of philosophers, not least Kant, and they in turn have shaped the way we do theology. So clearly, if there's a change in the physics, the underlying physics, that will in turn have an impact on, or should have an impact on, our philosophy of the world, and in turn on the tools with which we do theology. So I want to just introduce you briefly to some of the mysteries of matter. This is the paradox. So what is material and what is concrete and what is tangible to our senses, especially touch, is frequently regarded as setting the standard for what is most real and most reliably known. So, for example, in the Christian Gospels, to give one famous example, it's not surprising that the test that Jesus offers his disciples for the truth of the resurrection all involve touch, feel, matter. As is well known, material things and their acquisition have also become a measure of high or even ultimate value in many societies, especially in the last few centuries. And there was extraordinary critique of this by Solzhenitsyn. You'll maybe recall Solzhenitsyn spent years in the Gulag in the Soviet Union, and when he came to the West, people expected him to be, perhaps to some extent, to be praising the West, but he made this very strong critique at the Harvard commencement address in 1978, and it's worth just reading it a few lines in full. The turn introduced by the Renaissance was probably inevitable historically. The Middle Ages had come to a natural end by exhaustion, having become an intolerable despotic repression of man's physical nature in favour of the spiritual one. But then we recoiled from the spirit and embraced all that is material, excessively and incommensurately. The humanistic way of thinking, which had proclaimed itself our guide, did not admit the existence of intrinsic evil in man, nor did it see any task higher than the attainment of happiness on earth. It started modern Western civilization on the dangerous trend of worshipping man and his material needs. Everything beyond physical well-being and the accumulation of material goods, all other human requirements and characteristics of a subtle and higher nature were left outside the area of attention of state and social systems, as if human life did not have any higher meaning. And to sum up, he was really saying the Soviet Union and in the West at that time, they were really, the main difference was the different manner of worship of a false god. And this shift in culture and ethics towards matter as a first cause of human value can also be seen in the role of matter as a first cause in some philosophies. And such philosophers, you can call them the spiritual heirs of Thales, one of the pre-Socratic philosophers. He said that everything is made out of water. That was the first attempt to try to reduce all of the complexity of the physical world down to one material principle. And such philosophers generally called materialist. The slightly more subtle term is normally today physicalist. And the relationship between these terms is a matter of ongoing debate. But the general thesis of these approaches to the world is everything is material or physical, or as contemporary philosophers sometimes put it, that everything supervenes on or is necessitated by the material or physical. So matter is important. Matter is important for value, it's important for culture, it's important, it's regarded almost as a first principle in a lot of philosophy. But what exactly is matter? So here's a typical working dictionary definition. Physical substance in general as distinct from mind and spirit. Or in physics, that which occupies space and possesses rest mass, especially as distinct from energy. Notice actually in these statements that matter is being contrasted with something else. I think it's what some philosophers call a trouser word. You don't understand one leg of the trouser without understanding the other. It's a distinction from something else. Matter is a remainder, it's something left over from other things. Now, at first, it might seem that modern physics is intrinsically linked to a world that prioritizes matter. Matter, materialism, experimental science, all these things sort of linked together in the mind. But the role of matter in physics, as it's developed, particularly from the time of Newton, is more paradoxical than it might seem. And to take the archetypal Newtonian system, a planet orbiting the sun. You've got one big massive material object orbiting another big massive material object. The first simplification a Newtonian makes is to treat both objects as point masses, mutually attracting point masses. The matter, the stuff, fades out of consideration. And nothing matters about the matter except insofar as it contributes to resistance to acceleration. We model these complex systems as points orbiting one another in space. Everything measured, everything calculated, everything predicted is actually formal. And future states are reducible to present states by formal calculation. And that, of course, was what gave Newtonian physics such extraordinary power and also cultural power in society, because we are able to predict the future states of the solar system in terms of their present states. Now, what about the analysis of matter itself? So we've got this issue in Newtonian physics that material things seem to be prioritized, and yet at the same time it's the form that matters. It's the form. Mathematical states, positions in space, quantitative measures. If you open a modern physics textbook, you see numbers after numbers, calculations, everything's very formal. But what about the matter itself? If everything's reducible to matter, what do we find out when we study what matter is, and especially what matter is made of? So in this arena also, the notion of matter is inert, senseless substance, in which extension, figure and motion do actually subsist, definition from Berkeley. Well, that dissolves as a chimera upon investigation. What is matter made of? Every piece of matter reveals itself either to be composite or elementary to the best limit of our instruments, which we can go down to about 10 to the minus 17 meters. But what is elementary behaves as if it's point-like, albeit with a surrounding zone of attraction or repulsion to other elementary particles. A figure is often forgotten, being somewhat rehabilitated today. Is actually a Jesuit priest called Roger Boscovich. And actually, this was his theory of the philosophy of nature in 1763. It's one of the diagrams from his notebook. What's extraordinary about this is it looks like a modern physics textbook. And particularly, there's a curve up here, which is actually the kind of curve you'd find in a book of modern field theory. But the basic point is that the atoms are being modelled as points with forces. And the forces get very repulsive when the atoms get close to another atom, and they get attractive further away. But in the sense that all of matter is then modelled as points and forces and fields. And this is what then developed by people like Joseph Priestley, Humphrey Davy, and Michael Faraday. Exotic states of matter. The notion of matter being extended stuff, the everyday sort of sense of matter being extended stuff, is also called into question by some of the more exotic states that we now know of. So we predict, for example, that under extreme conditions, the forces of repulsion that keep matter extended can actually collapse. Atomic orbits can collapse to form what are essentially giant nuclei several miles across, which are neutron stars. In a neutron star, which is the densest stable form of matter, all the electrons' orbits have collapsed, and you've just got nuclei pressed against one another until it's just one giant nucleus, several miles across. But you can go further. Under even more extreme conditions, the nuclear repulsive forces can also be overcome by gravity, and then something happens. We don't really understand exactly what, but the surface of the star vanishes beyond an event horizon, and we get a black hole. So these things which seem solid, the matter seems so solid, can it's actually almost implode and actually almost vanish out of the observable universe. And similarly, on a much smaller scale, the elementary particles that seem most solid, the building blocks of matter, can be transformed into more ethereal objects of the physical world, such as photons or neutrinos under some circumstances. So matter, quite extraordinary. 150 years ago, if you said the whole universe exploded out of a point, people thought that you're crazy. This is now the accepted picture of how things came to be. It should still cause us wonder. The wonder has been somewhat lost by familiarity, but it's still absolutely extraordinary. All this stuff exposed out of something which is initially infinitely dense, or so dense that time and space themselves cease to have meaning. And similarly, as an artistic representation of a black hole, matter can also implode as well. So just summing up this part, matter, and especially what is measured by physics, has secured a position of a kind of first principle of being, of knowing, and of value in our society. Immaterial formal things, ideas, relations, souls, are held to be reducible or supervene on material and physical things. But paradoxically, however, it's become steadily less clear what matter is, or what role it plays in physics, other than exemplifying form. So eventually, some people spend all their lives in theoretical physics doing calculations. What are they calculating? The maths takes over almost completely. The notion of matter as extended stuff turns out to be peculiarly illusory when one asks where ultimately is extension. Physics in the tradition of Newton also has little or no use for matter ultimately, except insofar as it contributes in some aggregate way to sets of formal properties. So the paradox is we've reduced everything down to matter. Matter itself seems to reduce down to what? Form? Relation? I heard one theoretical physicist describe it as twisted vacuums. Okay, so we'll set that to one side for a moment. We'll now look at another mystery, which has become important in the last few decades, the mystery of chaos. I think, to some extent, a lot of people who do work in the philosophy of physics spend a lot of time looking at the difficult issues in quantum mechanics and so on. But there's a heck of a lot of ordinary mystery in much more basic systems. And it's worth going back initially to look at what Newton did and what he didn't do. Newtonian physics radically changed our worldview, and enabling the complex motion of each planet in an orbit with a few minor divergences to be explained in terms of a few simple mathematical laws. So all these complex objects in orbit reduced down to the law of gravity, inverse square law, capable of integration. We can predict where Jupiter will be in 1,000 years' time. It's extraordinary. But Newton's failures are less widely known, and I have to say I got up to doing a doctorate in physics without ever being introduced to this. He tried to apply his techniques to a more complex case, the Sun, the Moon and the Earth, and he found he could not integrate the equations. And since the 19th century, it's now known that such integrations cannot usually be done analytically. There are special cases where it's possible. So he set this as a problem for his successors, and they tried and they couldn't do it. And then in the 19th century we realised, well, we can't really do it in any ordinary sense. Now, Newton's failure to extend his technique of integrating forces over time to more complex cases is masked in the case of the solar system, because a solar system can be modelled more or less exactly as a set of two-body systems put together. So you can take the Sun and each planet, the Sun and Jupiter, the Sun and Mars, the Sun and Earth, and you can compute those orbits separately, as if the planet's orbiting on its own, and then you can add the integrated behaviour together of these systems, and you more or less model the solar system fairly well. And we've also learned clever techniques to handle a few of the planet-planet interactions, called perturbation techniques, and that was one of the ways that Neptune was predicted and then discovered. To some extent, we can use similar techniques in other physical systems. We can use them to an extent in atomic physics, because again, almost all of the most powerful forces are directed towards the nucleus, so one dense point in the middle, and the electrons can be treated first as interacting with the nucleus on their own, and then we can introduce the electron-electron interactions as perturbations. So we can play the same kind of technique with quantum physics in the atomic nucleus. For the nucleus, it's almost impossible to play this game, because the interactions are too strong with all the different particles together. So with the nucleus, we can't use the same technique, and we can't use it at all when we go to even smaller objects. The smallest known composite state of matter is the proton. Stable state of matter is the proton. The proton has 3 quarks, and it has quarks which themselves exchange particles called gluons. And in principle, we should be able to predict the behaviour of the whole object from the sum of the behaviours of its parts. And we can't do it. Even the world's most powerful supercomputers can't produce the behaviour. Brute force can help a little bit, but there's no analytic way to compute the behaviour of the whole from the sum of its parts. We can't use the Newtonian technique. So in the case of the solar system, just give you an example here. This is the individual planets. Each orbit can be computed separately, and then the behaviour of the whole is the sum of its parts. But that's not the case with a lot of systems in nature. Now, at least part of what made Newton's physics so attractive, however, is that its ability to make mathematical predictions of future states from present states of the system, linking past, present and future together analytically. It is hard to overestimate the importance of this development for our intellectual tradition. So, to give you one example, it is commonplace in physics and in a lot of the philosophy of science to treat time like space, because in this kind of system, time and space are almost interchangeable. So if you take a planet going one way around the sun, and then you reverse the time, and then you reverse the space, you end up with the system you started with. Past, present, and future states are symmetric. And because of this, it is now quite common to talk about space-time, to treat time as another dimension. And it tends to be forgotten the many situations in which it doesn't work. Now, starting from the 1960s and the pioneering work of Edward Lorenz, initially in the area of weather forecasting, it became apparent that some systems are different. They're radically unpredictable. And actually, this was discovered initially by trying to work out why an early computer kept producing different results in a simulation. And what was discovered is that a tiny rounding error, when the figures were put on by hand, created a hugely different result in the simulation. So, very small changes in initial conditions produced radically different changes in the output. A divergence is exponential over the time of the presentation. Now, what they were trying to do was weather forecasting, a very topical subject in Oxford at the moment. The initial conclusion was, well, we're going to have problems doing any long-term forecasting with weather, and that's still the case today. But Edward Lorenz then was very curious about its behaviour and began trying to strip it down to its absolute basic forms. And he discovered certain equations that were relatively simple, that he could study in detail. And the system described by the equations, isolated by Lorenz, also had another peculiar property. Classical systems, like a pendulum, they have attractors in a phase space which describes the state of the system. I'll show you a picture of this in a moment. But in the case of a pendulum, where you draw a graph of position and momentum, the motion of the pendulum can be described as a circle, and as the pendulum runs down, the circle gradually contracts towards a central point. And that is called an attractor in dynamics. Now, the simulated behaviour of the system described by the Lorentz equations also had an attractor, but one that wasn't due to the dissipation of energy. Repeated integration from any starting point in a phase space produces a trajectory that moves towards and then remains in the vicinity of two interconnecting regions of a phase space, a characteristic known as the Lorentz butterfly. So first of all, this is a picture of a classical system, like a pendulum, and you can see that gradually as the pendulum runs down, you get a spiral towards the centre of the system. That's the ordinary attractor, the point at the centre of the system. The Lorentz system is very different. I'm going to try to show you now a simulation of it, if I can manage to get it from YouTube. So one moment, please. Hopefully get this here. Lasts about 2 minutes. It's worth just seeing it. So this is describing this is a phase space. It will be like a pendulum in a chaotic system, and the point represents some initial state of the system, and the system's moving. The computer's calculating point by point how the system is changing over time, and it moves first to the vicinity of one state here. To explain something I'll touch on later, the computer isn't solving the equations exactly, because that's impossible. But what it's doing is doing an approximation, step by step, moving from one state of the system to the next. And in fact, until the invention of the computer, we couldn't really do this kind of work because of the huge number of calculations required. And you see, gradually, as the orbits are traced out, the shape is beginning to emerge, and it will gradually produce this characteristic butterfly shape, the Lorentz butterfly. Now, a couple of curiosities about this system. First of all, it doesn't matter where you start from. You can start from any point in the phase space, and the trajectories will always go towards the two wings of the butterfly. The second point about this system is that the shape it's tracing cannot actually be described analytically. We can get a general impression of it. When you analyse it in detail, it's what's called a fractal, and it reveals ever deeper levels of detail. It's not like a cube or a sphere. The shape itself has ever smaller and smaller levels of detail. A common example in nature that's usually used to describe this is the coastline. So if you look at the coastline, as you go to smaller and smaller distances, you get more and more inundations and so on. So if you want some fun with Lorentz simulations, there's tons of this stuff on YouTube. So let's get from here. And various other pictures of it here and here. And as is well known, we see phenomena in nature which look a little bit like, have something of the same dynamics. So even in what look like very unstable, very disorganized systems, we get order emerging. And here's a famous example that's lasted a few centuries, the red spot on Jupiter, a storm that's several centuries old, and amid all the extraordinary changes and instabilities of Jupiter's atmosphere, this remarkably stable structure persists over very long periods. The Lorentz system, and many others like it, exhibit therefore two remarkable behaviours. First of all, uncertainties in the initial positions inflate exponentially, but all points end up in the general vicinity of the strange attractor. So if you start 2 points in the phase space, they will diverge exponentially. And yet, all the points, wherever you start in the phase space, end up around the Lorentz butterfly. And to give an example of how strong this behavior is, I recommend, for all the details, a book called Explaining Chaos, Peter Smith. And so he gives us examples. So start with points, so almost exactly identical in the phase space, with a tiny error difference, delta x. Suppose also that both computers always calculate the pointers on the same wing of the butterfly up to time t, but then diverge. How much should the initial error be reduced to ensure that both computers produce the same result after 100 times the time? And the answer is 40 orders of magnitude, roughly equivalent to shrinking the entire distance from Earth to the edge of the observable universe down to the size of a proton. For all practical purposes, there's a breakdown of all predictive power. So even the tiniest change in initial conditions worked through the equations of the Lorentz system will end up producing points on different wings of the butterfly. So how should we describe such systems? And are they even philosophically significant? And a lot of people say no, they're just odd systems, very difficult to calculate. They've generally been called chaotic due to their lack of predictability. But this specification is not wholly satisfactory, and again I recommend Smith's book on this, since the same characteristics are also true of some ordinary classical systems. Moreover, chaos, the name given to the systems is chaotic, but nevertheless actually they're surprisingly ordered. Perhaps the most intriguing aspect of these systems is in any starting point of any trajectory in the phase space, all the points end up in the vicinity of the strange attractor. So though the position of a particular point rapidly loses predictability, all points end up roughly in the same vicinity. So I wanted out. So that sets the scene for the mystery of chaotic systems. Now I want to try to bring these two issues together. I said there's a lot written on chaotic systems, but I haven't quite so often seen the issue drawn, the connection drawn with the issue of matter. So when analysing Newtonian terms, a point moving in the phase space, that's the way we look at physical systems since Newton, a point moving in the phase space. The most apparent characteristic of a chaotic system is loss of information. We lose the ability to predict position. So treating a chaotic system in Newtonian terms, they're just bad news. But this choice of model is not accidental. This is the Newtonian tradition. This is the way we do science. Everything representing everything that's important about the dynamics of an extended body, such as a molecule or a planet in orbit, in terms of a single point, a mathematical abstraction called the centre of mass. I just want to cite here Professor Raymond Tallis. He wrote a popular article about points, and it gave me some inspiration to complete a paper on this subject. So, as Raymond Tallis pointed out, points are selfish. They have to borrow space from other things, such as dots or ink marks, which are not dimensionless, to even be represented visibly on paper or on computer screens. So points, they may look fundamental, but they can't be fundamental. They always depend upon other things for their existence. Now, consider what happens. The way we tend to think about, the way we tend to analyse chaotic systems is in terms of one point moving in a space. Now, imagine what happens if instead of a point, we consider a delineated region, a shape of some sort. What happens to the shape under the influence of the Lorentz equations? What happens to the points of a shape under the influence of the Lorentz equations? I gave some examples here. Imagine starting with all different stars in the phase space, like a triangle, a star, various other bits and pieces, or just a disordered set of points. And each point will take its own divergent path, but they'll all end up in the same vicinity of the strange attractor. Any extended object demarcated by a set of points in the phase space, configured in any form whatsoever, will be transformed into the wings of the Lorentz attractor. So consider from the perspective of extended objects, what seems clear is that initial information, the form of the initial shape, is removed systematically and replaced with new information, the form of the strange attractor. Nevertheless, the claim that all predictive power is lost, because that claim is often made about chaotic systems, we lose predictive power. But actually no, the attractor emerges, the final shape emerges infallibly, no matter how many times the process is repeated, and more importantly, whatever the initial structure. The initial structure is broken down, whatever it is, and replaced with that one structure at the end. So what's the principle of continuity between initial states like this and the final state of the system? Well, it's not true that there's no causal connection between past and future. So each point in some initial shape will match to some point in the final shape. Each point on the boundary of an initial extended object will eventually map onto some point in the general vicinity of the attractor. Now, of course, you can't see points strictly speaking, but if we adopt the standard heuristic of labelling them with the little identical dots, ink marks, not quite dimensionless, the overall volume of dots or ink used will be conserved between the initial and the final states. So if we double the number of points, if we halve the number of points at the beginning, we get half as many at the end. If we double the number at the beginning, we get double the number of points at the end. And the strange attractor will continue to be visible as long as there are some marks sufficient to demarcate its shape, the trail on the computer screens. So just to go back to this shape again, the only reason we can see it is because we're not looking at one point. We're looking at a trace of points through the space, and the many points reveal the structure. The shape only becomes invisible in the final Newtonian case, when the system is modelled as a single point in the phase space at the start of the process and a single point without a visible trail at future times, and it just becomes, we lose the final form. So this conservation, so on one hand, form is lost between the initial state and the final state of the system, but something is preserved between the initial state and the final state of the system. And this conservation suggests some principal continuity, but it has a peculiar characteristic. An answer cannot be given to the question of what this principle is if an answer is required in the customary manner of formal mathematical objects, like a numerical value, a position in space, or some determinate geometric form. I suggest that this principle is therefore properly called matter. What connects the initial state of the system and the final state of the system is nothing formal, but it's real and it's material. And I suggest that unlike the Newtonian system, for which matter doesn't really matter in connecting initial and final states, in chaotic systems matter does matter, and indeed this is the only principle of continuity between the initial and the final states. This is now a slightly more conceptually difficult step here. If we think of matter, how do we think of matter? Well, to get a handle on it with the mind, we normally think of it as a volume bounded by some limit. We might separate the limit and the volume. So it's impossible. You try thinking about undifferentiated stuff. Try thinking about matter without form. It's impossible. We have to give it a form, even mentally. But in the case of any well-defined geometric object, or an object translated through space, we don't really need the matter. The matter is like perhaps it makes the form visible, like a cookie from a cookie cutter. But the matter, in a sense, is superfluous, except to exemplify form. And that's true of Newtonian systems. Newtonian systems, the matter almost seems superfluous, except to reveal what the equations are already teaching us. But the need to distinguish what's different with the chaotic systems is that the form is eliminated, the initial form is eliminated and replaced with a new form. And there's no formal connection between the initial state and the final state, but there is a connection. And that connection you can think of as a continuity. You can imagine it as a volume, but not a particular bounded volume, because all particularity is formal. Now, that may seem strange, but it actually corresponds to how Aristotle, one of the definitions he gives of matter. Namely, that is as that which is in itself neither a particular thing, nor a certain quantity, nor assigned to any of the other categories by which being is determined, but which is known by means of the continuity through the generation and corruption of particular determinate beings. So, the matter is known through generation and corruption of particular determinate beings. In Newtonian system, the initial state and the final state are connected formally. In the chaotic system, it is the principle of continuity is not formal, but there is a connection, and that is the matter. And you can think of this in the biological, in many examples of this in biology, of course, it's what living things do. They take in stuff, all kinds of stuff from the world, in all kinds of different forms, and they transform it into their own form. And so what we're seeing in dynamics is a very similar kind of process now with these chaotic systems. We start with an initial state, and it's transformed into a final state. But the principle of continuity is the matter. A couple of objections, possible objections. So it might be claimed, and it is sometimes claimed, that the final state of a Lorentz system is formally reducible, at least in principle, to the initial state. So if we could get powerful enough computers, if we could do enough calculations, then we wouldn't really need any matter, wouldn't need anything else. We could connect the initial and the final states formally. And the argument could be made that such a reduction is possible because the information is still there, still available in principle, or even the fact that the computer can generate a representation of the strange attraction. The computer is a formal machine. It is actually doing just calculations. How is it able to produce a strange attractor if matter is needed. And in response, I'd first of all say, well, what's curious in the chaotic system case, the initial state doesn't matter. It doesn't matter where the point starts from. It always ends up in the same final state. Whatever distribution of points we begin with, we're delineating any shape whatsoever or no shape at all, they all end up looking the same, distributed around the strange attractor. So whatever the form of the strange attractor comes from, it doesn't seem to come from the initial configuration of matter, which is broken down in simulations. And a second response, if a computer is able to simulate a Lorentz system or other kind of chaotic systems, doesn't that prove formal calculations are enough? Because all the computer is doing calculations. And the response to this is that, well, the computers don't actually solve the equations. All they do is estimate a series of approximations. We get closer and closer to the final state, but there's always this causal gap. No matter how small the time slice of the system, the state of the system cannot be reduced analytically to the initial state. The computer reveals the general shape, but can never wholly compute it in the initial form, from the initial form. And so I'd like to modify a statement made from the early days of chaos theory, and a very influential article. It was in Scientific American, Chaos, published in 1986. I'll just read this out. So this is a statement by one of the early pioneers of chaos theory, wondering about the philosophical significance and physical significance of these new systems. The stretching and folding operation of a chaotic attractor systematically removes the initial information and replaces it with new information. The stretch makes small-scale uncertainties larger. The fold brings widely separated trajectories together and erases large-scale information. Thus, chaotic attractors act as a kind of pump, bringing microscopic fluctuations up to macroscopic expression. In this light, it is clear that no exact solution, no shortcut to tell the future can exist. After a brief time interval, the uncertainty specified by the initial measurement covers the entire attractor and all predictive power is lost. There is no causal connection between past and future. So that was one of the early assessments of chaos. In this article, the chaotic attractor is described as breaking down the initial information and replacing it with new information. Nevertheless, the claim that all predictive power is lost is incorrect, since the attractor infallibly emerges, no matter how many times the process is repeated and whatever the initial structure. In fact, the attractor can actually increase order as well as decreasing it. Moreover, it's not true that there's no causal connection between past and future, although it's impossible to see the connection if the system is analysed in Newtonian terms as a monadic point moving through space. The cause that connects the initial and final states is not formal, but material. Other implications. So the fact the Lorentz system tends towards a final state, and the irreducibility of the final state to the initial state also means, I think, that the final state of the system acts as an Aristotelian end or final cause. That is hugely significant. When I was at school, if Aristotle was mentioned in physics textbooks, he was normally laughed at. So they say, well, of course, we got rid of teleology, we've got rid of final causation, we've now got modern Newtonian physics. And suddenly it's coming back. All that stuff that was rejected is coming back. But funnily enough, we don't know how to name it because we've lost all that vocabulary. So we refer to emergence, complex system, something, whatever. But another way of thinking about this is Aristotelian causation in dynamics. And I suggest that the chaotic system is properly characterized not merely as teleonomical, because the final state isn't contained in the initial state formally, but it's teleological. And a chaotic system acts like a kind of Aristotelian pump or engine for breaking down and systematically replacing initial information that's present by a final form. And the only principal continuity between the initial state and the final state is a material one, hence matter matters. So a few conclusions and implications. Chaotic systems are usually being studied and even named from a perspective conditioned, I think, by Newtonian thinking, the trajectories of points in a space. From this perspective, their dominant characteristic is entirely negative, the rapid erosion of reliable prediction. This behaviour gave such systems the name chaotic, even though they actually change one kind of order, or even disorder, into another. If the study of these systems is considered in terms of changes to extended objects, then there's an irreducible final cause, the strange attractor, and a principle of continuity between initial and final states. This principle, however, is a material one in the Aristotelian sense, and not a formal one. How else does matter matter? As has often been remarked, chaotic systems don't undermine determinism directly, although the fact that the whole is not the sum of the parts in these models raises the possibility that natural systems may also exhibit causal behaviour that is more than the sum of their parts. But they do other things which are immensely important, and to this day I'm amazed at how little philosophers of science really pick up on these things. Insofar as they think there's a mystery, or many of them, they focus on quantum mechanics, but even ordinary mechanics has these extraordinary things in it. So they break the Newtonian system of past and future, reintroducing an arrow of time. So the final state is not symmetric with the initial state. It's not just in entropy that we have an arrow of time. More subtly, these neo-Aristotelian systems can also be said to unfreeze time, insofar as a future state is not merely a mathematical function of a present state, a characteristic of Newtonian physics that has a tendency to turn time into space. And if you read as a book, Lee Smolin, The Trouble with Physics, as a theoretical physicist writing about problems in contemporary physics. And there's only one diagram in the book towards the end, and it shows a chart of space and time. And then he writes a comment underneath, "This is the smoking gun." This is where we've got to get past. We've got to get past this point. We represent time as space. We think of time as space. And we're failing to capture what's important about it. Sometimes that approximation works, but it's not the whole story, and it doesn't work in these systems. So how else does matter? Well, an influential pattern of thought in philosophy, in the humanities generally, and in the broader culture is the belief expressed by a litany that biology is reducible to chemistry, and chemistry is reducible to physics, with physics ultimately reducible to some variant of Newtonian formalism, all twisted vacuums. The older, more organic Aristotelian thinking has been held to supervene on this more mechanistic foundation. The value of chaotic systems in dynamics is that they're simple enough to study exhaustively and to challenge this assumption. These models are also idealizations, of course, of nature, but they show that the Newtonian idealizations are no longer the only story. Final causes of matter matter, and this fact should inform our philosophy and our theology. And a little theological final coda. Since God is immaterial in his divine nature, and because of the seemingly divine-like attributes of ideas and forms and mathematics, there's a constant pull in our culture, in many intellectual and spiritual traditions, to prioritize form and to regard matter as intrinsically unimportant or even suspect. And Christianity itself has undergone this several times over the last 2,000 years. Every now and again we've smashed statues, we've emptied out churches, we've made them very bare and formal. We suddenly regarded matter as unimportant or suspect or dangerous, not divine. If, however, matter matters in dynamics to enable substantial change from initial and final forms, perhaps it's also time to reassess the importance of matter even in matters of the spirit. We cultivate changes to the soul, we can't manufacture them. And the soul is the form of the body in Thomistic thought. And we cultivate changes to the soul by means of sanctified and sanctifying matter. The perfection of the soul may be the end, but as the early Christian writer Tertullian remarked, it is the flesh that is the hinge of salvation. Thank you very much.
Thank you very much, Andrew. It's really, really interesting. And I'm sure there's many questions, and we have some time for questions. So I will leave to Andrew to decide who asks the questions, and then he'll answer, and I'll be passing them around.
Yes.
So,
Okay, I think the lady here is first.
sorry, if you can wait for the microphone to...
I've forgotten about that, so sorry. Yeah.
There you go.
Is the idea of antimatter still valid and or still fashionable? And if so, how does it tie with your whole theory?
Oh, so that's an interesting question. Is the idea of antimatter still valid and fashionable? Yes, indeed. In fact, we even produce it. So we can produce it in laboratories for short periods. We can smash antimatter into matter. Yeah, it's as real as matter is. But in a sense, it helps to underline the mystery, because if we take antimatter, and by the way, antimatter is, how do we describe it? It's matter with all the properties reversed except mass. So if you've got an electron that's electron has a negative charge, its antimatter partner has a positive charge, and all the other properties are reversed. If you bring these two together, boom, it just annihilates into nothing, energy, whatever that is. So yes, so antimatter is very important, but its existence helps to underline some of the mystery of matter itself, and where this thing comes from, and what it really is. I should underline that also one of the big mysteries in present-day cosmology and particle physics is why there's a disproportionate amount of matter and not antimatter in the universe. So one of the things that puzzles physicists today is, and there are many questions like this, is where do the asymmetries come from? So we expect things to begin simple and symmetric, and then suddenly they end up a bit skewed. You get almost the whole universe becoming matter and not antimatter just as well. And you get, someone described once to me, the universe is weakly left-handed. So you get particles which only exist in one kind of have one kind of rotational symmetry, not another. It's very that the human body processes only certain kinds of sugars, but not their mirror opposites. So that's one of the big mysteries. So where do the asymmetries come from? Yes, yeah, let's jump in there.
So can the unpredictability of chaotic systems, such as the human brain, get us free will?
Oh, gosh.
In
yes.
2 minutes.
2 minutes, okay. I wouldn't be quite as bold as saying that, but what I would say is that, chaotic systems introduce more pieces to the puzzle, and they don't allow us to reject free will on the basis that everything's reducible to Newtonian system. I think that's the best way of putting it. So they don't show that there's free will or spontaneity or any of the other fun things in themselves. And of course, the simulations we do are still predictable and so on. But what they do is that they show that that they help to counter this litany that's been part of our culture. Biology is reducible to chemistry, chemistry is reducible to physics, and physics is just bits of matter bumping into one another in a big box. There's more kinds of causation going on in the world, and things can be more than the sum of their parts. Once you get the idea that things can be more than the sum of their parts, maybe the rhinoceros is moving its own atoms, not the atoms moving the rhinoceros. If you just add one more point on this, I remember there's a book called Insight by Bernard Lonergan, which gives a very interesting example of this. But it points out that when an atom becomes part of an extended body, like a rhinoceros, it's no longer behaving like a free atom. All our laws of physics are for free things moving in a vacuum. They're idealized cases. Once an atom or anything else becomes part of a body, then it's not behaving like a free atom. My atoms are all assembling in front of this lectern. That's weird. And if you can imagine the carbon atom on the tip of a horn of a galloping rhinoceros through the plains of Africa, that's not behaving like a normal atom. It is behaving like the atom on the tip of a horn of a galloping rhinoceros through the plains of Africa. So matter behaves differently when it's part of forms. Causation, I would suggest very strongly, can go downwards as well as upwards. Maybe similar. Alan. Yes.
Thanks. I'm going to have to restrain myself with a long train of inferences and just ask you a question instead. But I was really fascinated by by the quotation from Aristotle that you gave, that matter is known by means of continuity through the generation and corruption of particular determinate beings.
Yes.
I mean, that really does seem to make more sense in the light of your presentation. But what seems to be going on then is, say, well, it appears to me at least, that what's going on is that the relational characteristics of a scenario come to be dominant features of a system rather than the substantial, absolute, almost want to use the word material parts or elements of the system. And that's not to say that the word material there is used in the Aristotelian sense, it's just used in the kind of colloquial sense. And so I'm wondering whether there isn't a real need to get to grips with what relational being actually is, recalling that Aristotle had trouble categorizing relational being, seemed vaguely to notice that some forms of relational being are mind-dependent and not mind-independent, so they wouldn't fit into his categories. And of course, after that came the whole Latin age with all the discussion of, you know, relational being and all its varieties. Is there a good and quite a real need to get to grips with what that might be and how that might bear on matter?
Well, we always have a problem getting at anything which is not formal, with the way we think about things, because the mind abstracts, and it also freezes in a sense. So, and actually, this touches on a big issue in neuroscience, and one of my favourite authors, the Ian McGilchrist book on the divided brain and the making of the Western world, particularly in our modern culture, we seem to use part of the brain that really freezes things formally. And certainly you can see this in mathematics, in physics, in culture. Everything if you look up an encyclopedia article on a country, you'll find facts and figures. You'll find numbers everywhere. You open a physics textbook, you find numbers everywhere. We get quantitative relations pretty well nailed down, and we can do that brilliantly. You know, we can measure most extraordinary things, tiny corrections of orbits of electrons to 1 part in 10 to the power 12. We're good at that sort of stuff. But what Aristotle picked up, and what I think we are neglecting, is that material thing which is elusive to that mode of analysis, and we know it principally through substantial change. So and that's why I think the Celtic systems are important. Matter will always be elusive to us in some sense because we have to abstract. We get a form, but we can see its work in the changes in the world. Oh, I think I'll leave back there first, probably. Yes.
Thank you, Andrew. Quite mind-expanding talk. I'll start with a quip, which I rather like, which is, what is matter? Never mind. What is mind? No matter.
No matter. Yes.
Which you might recognise.
Thank you.
Use of English there. But when you put up that Lorentzian butterfly, I saw the symbol for infinity. And I thought, that can't be an accident. Somehow, we have that symbol handed down to us, where has that come from? It's just, just the symbolic nature was just far too strong. And you've already touched on the point I was going to make, which was an intrinsic duality at the heart of existence. And that, Lorentzian butterfly seems to demonstrate that. As the previous speaker said, all things in relation, all things in movement and in relation to one another. So as you said, the atoms in your body are behaving in concert in relation to one another. So if you want to comment on symbolism, perhaps that might be useful.
Yes. Well, in regard to relation, I think I really want to underline the distinction being made in these new systems, because we can relate, and that's what is so remarkable about Newtonian physics, is being able to relate the future to the present. But the manner of that relation is itself formal. So we can reduce down the future to the present, even by a purely formal mathematical relation. What I think what makes these systems interesting is that the matter is what connects the present and the future related through the matter, and not just through the form. In fact, they can't be related through the form because the form is broken down and replaced. And that's weird. That will take a while to sink in, because it's we haven't been thinking about the world like that for a long time, and I think it's a great need. As a former physicist myself, I'm sorry these questions are not asked enough about the nature of space and time, the nature of matter. There has been actually for a few decades of just get on with the calculations. And I think that's now beginning to be detrimental to our ability to advance in physics. And so that's why I do recommend, if you're interested in this particular topic, Lisa Molin's book, The Trouble with Physics, as a theoretical physicist, looking at these, trying to think his way out of the box. Yes.
Thank you, Andrew. You mentioned at the beginning of your talk that ancient theories, such as Thales' theory that all is water, are referred to as materialist theories, and that there's this more subtle term, physicalism. And then you told us an awful lot about what matter is and what mysteries there are related to it. Another question, obviously, is what the physical is, or what it is to be physical. And it's an extremely important question in relation to what came up earlier in relation to free will. Obviously, one of the big problems people present for free will is the causal closure of the physical. How much of a problem that is and what kind of problem it is depends on what we mean by the physical. So I was wondering if you could say something about what it is to be physical,
right,
as opposed to merely material.
Right. Well, I mentioned briefly at the beginning that there is an argument in philosophy about the distinction between materialism and physicalism. And if you want a brief summary of this, the Stanford Encyclopedia of Philosophy article is very good on this. Goes through all the different options. It's very complex. But you might regard it as generally a kind of slightly different emphasis. So if the materialist is reducing things to extended stuff, the problem with that is that too much that is included in the world of physics is kind of weird. It's not extended stuff. I mean, what is a gravitational field? Is that material? What about a photon? Is that matter or what? So physicalism is more often used as a term these days, and with slightly different emphases. And there can be a bit of a cop-out statement. The cop-out statement basically is reality is whatever the physicists tell us it is. Except physics includes a lot of weird stuff, which a lot of stuff which isn't really material, and that was actually even in the early days of Newtonian physics. Action at a distance, already we begin to introduce very strange things. So I suppose what you got with the battle of these ideas, materialism and physicalism, is the desire to get everything that science says is respectable inside, but science says things are important which actually are pretty weird. So So that's why part of that battle is going on. As for generally the connection between the issues in physicalism and free will and so on, I think what I would make a plea for is just a very generous notion of the term physical, because the problem we have, and we've run into problems with things like free will, when we take a very restricted notion of what the word physical means. If we say that everything is reducible down to a Newtonian two-body system, and Newtonian two-body systems are calculable in the future from the present, it seems hard to get any kind of spontaneity and change. But we don't have to play that game. And dynamics today tells us we don't have to play that game. So it's not so much physicalism which is a problem for free will or anything else. It's when you take a very restricted notion of what the physical world can be. So a typical pattern of the debates for the last few centuries has been, I'll create a toy universe with only a few ingredients. You see if you can get free will and God out of that. And you can play that game, or you can decide to play a different game. But what helps to break the spell? What helps to break the spell that that's the only game in town is to look at the actual physics itself, and you see, well, there's a lot more in the shop than these simple systems. Yes, a gentleman there, I think.
The shape of the strange attractor, doesn't come out exactly identical each time, or?
Oh, that's a good question. Yes, it never comes out absolutely identical, and it can never be traced absolutely precisely. We can't get the exact form because it's not actually analytic. We can't describe it by an equation. We can only trace its orbit, its general vicinity in space. And its vicinity forms a fractal, this peculiar self-referential surface where you get ever greater levels of detail. So all you get is a sort of impression. But it's still there, and it's always there, and it always appears. Yes.
After Einstein's discovery, we know that matter and energy can be transformed into one another. Do you take that into account?
Well, yes. It's people have different interpretations of what Einstein meant by that. Another way of saying it is energy has mass. But certainly it seems that things we regard as material, like matter and antimatter, can be transformed into nothing there except energy. So there does seem to be an ability to transform these things. Where Einstein's perhaps most important in this whole area is his basic insight that space and time are not fundamental, that light is more fundamental than space and time. And it's always important to remember he began by daydreaming during his job and asking the sort of questions a child might ask, except except people were not asking them. Like, what would it be like to ride on a beam of light? And if he was riding away from the clock striking 3 on the light, it would seem as if the clock always stayed at striking 3. So time seems to stop. I asked a question actually in a lecture a few days ago. If you look out into space and there's a glow across the whole night sky, the cosmic microwave background radiation, we interpret that as the after echo of the Big Bang. It's one of the strongest pieces of evidence we have for the Big Bang. Now, a question I asked: if you were riding on a photon, if you were riding on the light that's reaching us from the Big Bang across 14 or so billion years of light years of space, how much time would have elapsed if you were riding on the photon of light? Any thoughts on this? If you rode on a photon of light from the Big Bang to reach us, sorry? No time. No time. It's amazing. I use this, by the way, as a counter to the Kalam cosmological argument, because people say, well, you know, the universe has a beginning, but if no time is passing from the point of view of a photon, how can you say it's begun? But the thing is that Einstein taught us that there are things more fundamental in space and time, but we haven't really absorbed that insight. And we've actually gone back to, we've almost tamed it and got back to thinking exactly the same way as we were before. We treat matter moving in a box, except we stretch the box, but we just carry on as before. And we've mathematicized his insight, and then we've gone back to thinking about the world more or less before his work. So I think that's the more fundamental insight we need to tackle from Einstein. Must remember, just kind of follow that with one more point here. But the big battle, the big struggle of the last 23 centuries has been to work out what things are in change and what things are constant. The big work of philosophy has been to work out, to explain change, what things are change and what things are constant. And people have had different views about what the constant things are. So back in the place for Plato, it was the forms. And for Aristotle, the centre of change is substance. For most of the last few centuries, it's been space and time. So if you look at physics equations, always written with respect to space and time, as if there's a thing within which we move. And it's a good model for a lot of things. But there are physical phenomena where it just doesn't work very well. But it's become so real to us. We even teach children Cartesian graphs from a very young age. We teach them to think about the world as a box within which things move. And we've now discovered, even in physics, that there are situations where we just can't do that. Yes?
Thank you very much for your talk. You said that since God is immaterial in his divine nature, and because of the seemingly divine-like attribute of ideas form on mathematics, there is a kind of, this notion of incarnation. If God is, in his divine nature, is not material, in his incarnation,
right.
is material,
thank you. Yes,
then, I'm sorry, the question is, do you think that also, as he is the first cause of everything, that he make interconnection between matters and continuation between matters also?
Right. So what I was referring to there is that every now and again, including, yes, Christianity is an incarnational religion. We put it's very unusual to put belief in the one God who's immaterial in his divine nature, together with matter. And this is what's so unusual in the sense of in the Christian tradition. But every now and again, we revolt against that idea. So I think it was 7th, 8th century Constantinople, they smashed all the icons, they got rid of the matter, they tried to strip all these things away. Same thing happened in 17th century Europe. If you go to places like York Minster, you'll see that the statues in the alcoves have all been smashed. We have this tendency every now and then to get rid of matter and to approach God as if like purely in a formal sense. It doesn't tend to work out very well. And yes, of course, the Christian, the base of the Christian faith is this idea that the God who is immaterial in his divine nature has come to us also materially through the incarnation, and has provided a kind of bridge between God and ourselves. And in that sense, also the flesh is a hinge of salvation. Oh yeah.
Thank you very much. That was really, really interesting, Andrew. You spoke of bringing a new Aristotelian understanding of nature, and so far I agree on that. We both know that. And you spoke that the phrase, the chaotic systems give us a hint towards understanding matter again in Aristotelian terms. And I think I could agree with that, not knowing much about chaotic systems, but it seems like, yeah, change, corruption, in Aristotelian terms. So matter is that which underlies change. Great. And then you spoke as well a lot about forms. And it seemed to me, and I wonder whether you can tell me something about this, you moved from different notions to different notions of forms. But I'm not sure if that is the actual case. At least that's how I understood it. In the following sense, you spoke of forms as mathematical structures, which is not exactly what Aristotle thinks of forms at all.
That's right.
Or even not just mathematical structures, just shapes, or shapes, diagrams, structures, mathematics involved. So can you say something about
thank you.
those two notions?
Thank you for picking me up on that. Yes, you're right. I was being deliberately broad brush. Although even Aristotle was prepared to use a few geometric forms to describe form every now and again. The material that makes up a statue will be the famous example of that. So the problem with all these things, we do have to use imperfect examples, and there is a danger of treating form in a geometric sense. That's true. And that shouldn't be understood, because form, though how to define form exactly is also very hard. In fact, we often need different examples from different directions. One brief way of thinking about it, the intelligible constitution of a thing. So we can define it in terms of what we can grasp with the mind. We can't grasp the matter, but we can grasp the matter through the change of form. So that's, again, it's a slightly cop-out way of doing it, but it's the intelligible constitution of a thing. I suppose, but what I would say, I would defend the use of the mathematical examples, but I would agree to add a health warning. That's not the whole story. Okay.
Good then.
Perhaps I can add a final comment about add a comment of spirituality, because I mentioned towards the end we cultivate changes in the soul. I spent 7 years at seminary, and they made us do morning prayer and evening prayer, and morning prayer and evening prayer, and morning prayer and evening prayer. I mean, mass every day, mass every day. And I would have thought it would be very nice to be able to manufacture holiness at the end of the day. Just press a button, get the. It would be very nice to sort of mass produce holy people if you just get the form right. But actually, attempts to do that, and there have been people who try to do this, attempts to do this tend to come to grief. And one thing I learned from these practices in the seminary, the spiritual life has to be cultivated. So as a final pastoral note to those of you who have faith or searching for faith, it's the daily practice that matters. We have to cultivate changes of the soul, and maybe we're given matter precisely to enable us to do this change, to have time, and to come to our proper and final fruition. Thank you very much.